Good morning, everyone. Welcome to this Copernicus Marine Service training workshop dedicated to the Arctic Ocean. My name is Ergane Fouchet. I work at Noveltis, and I'm going to be animating this session with F.Messal. Hi, Fabrice.
Hi, Ergane. I'm very pleased to be with you today. Thank you for joining us. So this is the second day of our training event dedicated for the Arctic Ocean. Today, the session will be dedicated to practical and hands-on exercises prepared by our experts. So I'm F.Messal, UX and Capacity Development Manager at Mercator Ocean International, and I will be with Ergane Fouchet, Oceanographic Engineer at Noveltis, your moderator of this session. So welcome to this second day of the training workshop. Let's dive into the program and the technical information. So you can have access to a lot of material on our Padlet. The link will be shared with you on the chat of the Zoom. And you will see different kind of information with the participant manual to access the different links we're going to share during this session. Some tutorial videos to learn how to register, to get started, and links to the e-learning material available on the Copernicus Marine Service website. And you will have also the video of the presentation of the different products from the day before, and some links to the use cases presented yesterday and new use cases related to the Arctic region. And on this Padlet, we have a feature to pin your location on a map and to see where you come from. So let's check the map of yesterday attendees. So yeah, we have a lot of people in Europe, obviously, but also from other countries like United States or India or Indonesia. So welcome all of you. Let's start on interaction rules. Let's talk about international interaction rules. So we are on Zoom meeting. You have a chat available, but it's only for small talks. After each presentation of our experts, you will be able to ask questions on Slido. The link to the Slido for this event will be shared with you on the chat. So don't hesitate to ask your question. You will see on Slido you have the possibility to sum up a question if you are interested, and we will ask some questions to the experts during the session. Today, the agenda is very simple. You will have practical session. We will start with Ergane, who will present a Jupyter notebook. So this is a Jupyter notebook dedicated for beginner people. You will learn how to access the data with the different protocols available on the Copernicus Marine service, and make some basic operation to create maps, profiles, etc. And then after a coffee break, short coffee break, we will have a demo of the MyOcean viewer with David, and you will learn how to add a new layer, to modify the color bar, to dive into the data, thanks to this very powerful tool, which is the MyOcean viewer. And then at the end, you will have a QGIS session animated by Etienne, and you will learn also some basics to play with the data into this GIS tool, which is QGIS. So I think that's fine for me. It's okay for me. So now we can start with Ergane, who will show us how to dive into the data, how to play with the data with the Jupyter notebook dedicated for beginner. Ergane, the floor is yours.
Thank you, Fabrice. Can you see my screen?
Yes.
Okay, great. So just like Fabrice said, we have developed several exercises for this training on the Arctic Ocean. I'm going to present you the exercises on Python and on the Jupyter Hub. You can access the Jupyter Hub from the Padlet in the e-learning materials section here. You have the Jupyter Hub access. If you click there, you will reach the Jupyter Hub. You may need to enter your credentials before entering the Jupyter Hub. And so in the shared notebooks directory here, you will find all the Python material we have developed for the previous training. So the one on the global ocean in Africa, America, and Asia, as well as the workshops on the Copernicus region. So the Arctic, the workshop from 2020 and 2022. This is the one we're having today, and also on the Baltic Sea and on the Mediterranean Sea. So as I said, the workshop the material we're interested in today is the Training Arctic 2022. And as you can see, you have two directories. You have one that refers to the beginner exercise, the exercise dedicated to beginners. If you don't know anything about Python, the Copernicus Marine Service products, and the Jupyter Hub. And you also have a second exercise dedicated to intermediate level users, which covers a real case scenario, which is the thermohaline circulation in the frame of climate change in Arctic. So in this session today, I'm going to present you the whole exercise dedicated to beginners. The second one, the one for intermediate level users, has been recorded on video and is already available on the Padlet. The first thing to do is to copy the directory of the Jupyter notebook into your home directory, because in the shared notebooks directory, you don't have the rights to write or to run the cells. So the first thing you need to do is to open a terminal, just like here, and to copy the directory, shared notebooks, training Arctic 2022. And then if you run this command line, the whole directory with all the material from this workshop will be copied into your home directory, and you'll be able to manipulate the Jupyter notebooks just like you want. So let's start and let's open our Jupyter notebook. So this is what a notebook looks like. It consists of text, and you also have code cells. The code is in Python, obviously. If you want to run a cell, you can click on the arrow on the top menu here, or you can run the keyboard shortcut Shift and Enter. And if you have some trouble with the Jupyter notebook, if it stops working, you can try to restart it by clicking on the loop arrow on the top here. So we can start the exercise. I would just like to remind you that this session is being recorded, and it will be available on YouTube within a few days. And so I strongly encourage you not to do the exercise at the same time as I do, because it will be more comfortable for you to do it, to take your time and to post the video once it's online. So The program of this session, so first we're having this introduction, then we're going to present you the data that we're going to work with and how you can access the products, how you can download the data sets from the Copernicus Marine Service. Then we're going to see how you can explore the products with Python, and finally, how you can plot the maps, so the figures, the maps, the profiles, the time series, etc. So in this exercise, we're going to manipulate the product, the data sets, in order, and the objective of this exercise will be to analyze the Arctic Ocean condition in several different ways. So this is just an example for you to learn to manipulate the products. We are going to study the Arctic Ocean with 3 different Copernicus Marine Service data sets taken from 3 products: 1 model product, 1 satellite observation product, and 1 in situ observation product. The model product we're using comes from the Arctic Ocean physics reanalysis. If you click on the link, you can find the catalog, the web page of the catalog. You can find all the information on the product, its geographical coverage, its spatial resolution, temporal resolution. So plenty of information, and especially you can find the variables that you may be interested in. The satellite observation product we'll be using is the Arctic Ocean sea ice thickness preprocessed. Again, if you click on the link, you will find all the information on the product. And finally, the last product we're working with comes from an in situ instrument, which is a profiler, and we're going to study a salinity profile. It has been presented yesterday during the products overview, but the in situ products are not as easy to download as the satellite and model products. We have developed some notebooks in the previous workshop, the one that took place in 2020, for you to learn how to download the in situ products. So here you can retrieve the link. It will open you the link to the notebook, which enables to download the in situ products. I won't have time to go through all this notebook, but very briefly, how does it work? You load first a huge database which contains all the in situ observation on the Arctic Ocean, and then you apply some filters depending on the type of instrument you want, on the position, the time period, the parameters, etc. You apply all these criteria, and then you download the files that match your criteria. So this is what this notebook does. It's very, very well explained. I use it every time I need to work with in situ data. And so you shouldn't have any problem if you want to go through this notebook and download some in situ product. In case you encounter some difficulties, you can always ask us, send us an email. You have the email address at the end of the notebook, the service desk email address. And we will be very happy to answer your questions. Okay, so now that we know which products we're going to work with, we can see how we can retrieve them, how we can download them in order to manipulate them in Python. The first method, which is, in my opinion, the easiest method, the most user-friendly one, is to do it from the catalog. You have a tutorial video here, but I'm going to show you very briefly how it works. So if you click on the link to the catalog here, You can select the region you want. So here, for example, if we take the Arctic Ocean, let's take this, for example, we are going to go back to the information web page, and you have a section data access here. And if you click on the link of the subs, you will have to enter your credentials. And then you'll be able to subset the data set, selecting the spatial coverage, the geographical area you're interested in. So either the whole region or the sub-region. Here, for example, we can change the latitudes. You can select the dates. In some cases, you can also select the depths. And finally, you can select the variables. Then you can click on download, and the file will be downloaded on your computer. So that was the first option from the catalog. The second one, which can be very convenient, especially in Python, is to use the Motu client. So the Motu client works thanks to such command line. So the first line, you define the path to the Copernicus Marine Service, to the product and to the data set you want. You set the min and max longitude, latitude, dates, depths, and also the variables you want to download. You set the output directory, the output file name. You have to enter your username and password. And if you copy, change the parameters that are required, and then run this cell, the file will be downloaded on the Jupyter Hub. So this may sound kind of complicated, but if you have done your selection from the catalog, you can go to the download options here. Then you have view script, and the command line is generated automatically here. So this can be very useful, and the Motu client is also very useful, especially if you have to download several files, because you can change the variables into Python variables and create loops, etc. So the Motu client can be very useful. The third option is to do it from the FTP. It's a little more complicated than the other ones, but it's also very useful, especially if you need to download plenty of files. In the FTP, the products are, well, you can't subset, you can't apply any filter on the files. You will only download, you can only download the whole files. Usually it's one file refers to 1 day or 1 month of data. And so how does it work? Well, if you go through the notebook, you will have time to read the whole explanations, but you have to set your username and password. Then you connect to the Copernicus Marine Service portal. If we go to the data access here, you can retrieve the link to the FTP. So this is what you need to enter here. And the principle of the FTP is that you go through, if you want to use it with Python, you go to a directory, you list the files and directories which are in this directory, and then you change directory until you reach the netcdf file you're interested in, and then you download it. Again, the netcdf file will be downloaded directly in your Jupyter Hub environment. And so the last method to access the Copernicus Marine Service data is to use OpenDAP. In the previous methods, we had downloaded the files. So at the end of the day, we had a netcdf file either on our computer or on the Jupyter Hub. But the OpenDAP method enables to stream the product, which means you don't have to download anything. You just use it remotely. And it can be very useful, especially as the files can sometimes be very heavy. And if you don't want to download many files, then the OpenDAP solution can be very useful. Again, here, if you have the link to the OpenDAP, and if you click on API here, you can retrieve the link. I'm going to show you an example right after. So far we have seen which products we were going to work with and how we could access them. Now we're going to set up Python. So just like any other Python code, the Jupyter notebooks needs to be initialized with the libraries we're going to use. So here are the 4 libraries we will work with. The first one is NumPy, which is a very basic library in Python for scientific computing. We're also going to work with Xarray, which is the library we use to manipulate the netcdf files within Python. We are using Matplotlib for the figures and CartoPy for the maps and geospatial data analysis. Here you can find the links to the documentation of each library. These libraries are very basic. You can their documentation is very complete. Can we mute?
Can you
okay,
just
thank you. And so these libraries are very basic, and you can find plenty of examples on the internet, either on the documentation web pages or on the forums. So you shouldn't have any problem using them. And if you do, you do not hesitate to contact us. So first we are running the first cell to import the libraries. And then we're going to load the files. So as it has been said yesterday, all the files, all the products from the Copernicus Marine service are distributed in netcdf format. And so it's a very commonly used format of data. It contains dimensions, coordinates, variables, and attributes. We're going to see the difference between coordinates and dimensions right after. But what we need to know for now is that the variables depend on the dimensions. The variables are like the temperature, the sea ice thickness, etc. To open a file, an netcdf file within Python, we're using Xarray and the function xarray.openDataset. Here you can also find the link to the documentation page of the product. And so first, we set the path to the netcdf files. I forgot to tell you that all the data we're going to work with today have already been downloaded and are stored in the data folder here. It's the same for the second exercise, the one for intermediate level users. And so you have to set the path to the netcdf files you're using, and then you use the function xarray.openDataset with the path to open the file. So we're loading 3 data sets: the one that refers to the model, to the satellite observation, and to the in situ dataset. So we run this cell. Just before, I was telling you about the OpenDAP service. Once you have the link that we got from the data access section, you can use the function xr.openDataset just as you would for if you had the file downloaded. You just put the link instead of the path, and it works just the same. So we can now begin to explore the files that we have loaded. It's very easy in Python to see what a netcdf file contains. So here you can see we have stored the model in the Python variable, which is entitled mod. And so you just have to run the name of your variable to see what the dataset contains. So here we run mod. And so we can have a look at the dimensions. We can see that we have the depth. We have 40 values of depth. We have the time with 12 values, and we have X and Y. We can have a look at the coordinates as well. They are the same as the dimensions, except we have the latitude and longitude, which depend on X and Y. I'm going to explain you the difference between the coordinates and dimensions right after, especially regarding the longitude and latitude. And then you have the variables. So you have plenty of variables. If you click on the show hide attribute button here, you can find the attribute of the variables. So here you can see that this variable refers to the sea ice thickness, and its units are meters. You can also, for example, if you want to see the date times included in the model, you can click on the show hide data here, and you can find all the dates included in the model. You can see it goes from January 2020 to December 2020. Just to make sure that the OpenDAP works just the same as if you had downloaded the product, you can see we had stored the dataset from OpenDAP in the mod OpenDAP variable. And if we run this cell, you can see that it's the same, except that we have more time dates, because the file that I have downloaded had been subset. We had applied some filters not to download the whole product, whereas in OpenDAP you have the whole product. You also have all the variables, because I chose to download only a few, but here you have all the variables included in the product. If you want to select a specific variable and not to work with all the variables, you have two options. You can either, so first you have to retrieve the name of your variable. So for the sea ice thickness, we've seen that it was this one. And you can choose either to call it this way or this way. And if you run it, you can see that we used to have a dataset, X-array dataset, which means that it contains several variables. And if you only have one, it becomes a data array. And you keep the values of the coordinates, dimensions, etc., but you only have one variable. So that's the difference. And if you want to work with raw data, if you want to lose the data array format, if you just want an array, you can use the method .data, and then you can see that you only have the values, so the values of the sea ice thickness, for example. Okay, so now we know everything about the products, how we can access them, and how we can explore them within Python. So we can begin to study the Arctic Ocean and to begin to create figures. So in the following sections, we're going to see how to create these figures. The first thing we're going to need to do is to subset the data set. And so we will see two methods depending on what we want to select. Either, well, there are two different methods depending on if you want to subset the dataset along dimensions or coordinates. It's kind of complicated because we're in the Arctic Ocean, and dimensions and coordinates are not the same, but I'll explain to you this right after. So let's say first that you want to subset the dataset along its dimensions. So we have seen previously that time was a dimension of the product. We can check if we have a look at this. we're now working with the satellite observation product, and we can see that indeed time is a dimension. So if we have a look at what the variable time contains, we can see that it contains 90 date times from October 2002 to March 2015. And so there are several options for you to select the dataset at one specific date. The first one is if you know the exact date, let's say, for example, February 2003, we can see that this date is indeed included in the dataset. So if we run this cell, you will see that the time is the right one. If you don't know the exact date, if the date you want to see is not exactly included in the dataset, you can choose to select the nearest date in the product. So you use the parameter method equals nearest. And so here, if we take the 10th of February 2003, if you run this cell, you will see that the time that has been selected is the 1st of February because it's the nearest date in the data set. You can also select a date time from its index. So if you take the fourth index of time, again, you will see that we get the date we want. Finally, the last way to use the .cell method is to, if you want to select a range of dates, let's say, for example, from January 2013 to January 2014, you have to use the slice method. And if you have a look at the time here, you can see that it indeed goes from January 2013 to January 2014. So thanks to this method, so now that we know how to select, to subset the dataset and to select only one date, we're going to be able to plot a map. And so we're working again with the model observation, the model product. And so this is a reminder of what the model dataset contains. We are going to plot the sea ice thickness. So we remember that it's stored in this variable. And we are going to plot the map. So for all the figures I'm going to create, I will first show you the results and then show you how it has been constructed. So this is the map that we are plotting here. It's a really pretty map, I think. It shows the sea ice thickness on August 2020. So the color refers to the sea ice thickness. Its units are meters. At the bottom, you have the color bar. And so let's see how we have constructed this map. First, we have selected the date. So here we set August 2020. Then we select the sea ice thickness, and we also select we subset the data set at the date we have defined. Then we create the figure. We define its size. Then we define the characteristics of the plot. So we add the coastline, which are the gray lines that separate the ocean from the land. We add the grid lines, so the latitude and longitude lines. We add the land mask to represent the land. And we define the extent of the map. That's it. We are then using the function pColorMesh. Its parameters, well, you have to use these parameters the following way. You set first the longitude, then the latitudes, and then the values of the sea ice thickness. You set the color map. you set the min and max values of the color bar. So you can see here it goes from 0 to 3.5 meters. And that's it. You add the color bar. Here I've chosen to put the orientation as horizontal. We add the title of the color bar, and then we add the title to the figure. So this is what it does. So we can see that in August 2020, most of the Arctic Ocean was free of ice, and the region where the ice was the thickest was in this region. Here is an exercise you can do if you want to manipulate and to learn to use the Python script. You can try to change the min and max values of the color bar. You can change the color map. You can also try to display another parameter. In this data set, you have other parameters. So you can try, such as the salinity, for example. You can try to plot the map of the salinity. And you can also make a zoom, so change the extent of the map to see a specific region. So in this section, we're going to see the specificities of the polar products. This is what I was talking to you about, the difference between the dimensions and the coordinates. If we go back to the product information web page, you can see that in the characteristics, you can see that the coordinate reference system is polar stereographic north, which means this is what says that the dimensions of the product will be X and Y and not longitude and latitude. If you compare to a global model, for example, you will see that we have another coordinate reference system, and this one says that the dimensions will be longitude and latitudes. We are doing this, so the text explains plenty of, gives plenty of information, but very briefly, here is an explanation on why the grid is different. On the left, you have the grid that is used, so the coordinate system that is used in the polar products, and on the right, you have the grids that are used in the global products. As you can see on the left, so for the polar products, we have a very homogeneous grid. Whereas on the right, on the global ones, we have much more, the grid is more finer, it's much finer on the highest latitudes than in the lowest ones. And this is something that is not very convenient if you want to work in the polar region. And so this is why we are changing the coordinate system in the highest latitudes. So as you can see here, the number of points is not as dense as at the very north. There are several ways to display a map in Python thanks to CartoPy. And so to change the projection of the map, you can find the list of the projection in the CartoPy documentation webpage here. So you have plenty of projections that you can use, which are more or less convenient depending on the region you're studying. And so in this notebook, we recommend 3 projections, which are rather convenient and relevant in the North Pole. So we have the North Polar Stereo, the stereographic one, and the near side perspective. in the first one, you have to set the central longitude, but the latitude will be automatically 90 degrees. In the second one, you have to set the central latitude and longitude. And in the last one, you can change the satellite height, and it will show you the Earth as if it was from a satellite. So here is a short script to show you the difference, the result between the three projections that we suggest, depending on what you prefer. You can use one of these three, or you can also use the other ones if you prefer. So before in the first section, I was talking to you about subsetting the dataset along dimensions. Now that we know how to do it with dimensions, we will learn how to do it along coordinates. And so I'm going to go back to this map. The aim of this section will be to find the closest point on the grid from a point you have defined. So let's say, for example, you want we're going to set the coordinates of one point. So we will set its longitude and latitude, and we will have to find the closest x and y, which give the location, the longitude and latitude location, the closest to the point we have defined. So how do we do this? So as I said, you set the coordinates of the point you want to retrieve. Then you calculate the distance of all the points of the grid to this point, the one you have set the coordinates. You calculate the minimum distance, and then you select the data set at the point where the distance is minimum. So it's more complicated than if it had been a dimension. But this small script will be very useful if you want to study a point, which is what we're going to do in the next section. So here you can see that we have selected the longitude of 42 degrees and the latitude of 85. You can see that it refers to the x, a specific value of x and a specific value of y. And the longitude we are having is close to 42, and the latitude is also close to 85. So this is a method for you to extract one point of the data set if you want to plot a time series, for example, which is what we're going to do now. So we are going to work with the satellite observation product. And we're going to select one point and to see how the sea ice thickness has evolved at this point. How it has evolved. To do so, we're using the matplotlib function plot. So let's be reminded of what the satellite observation product contains. We remember that it has 90 date times. We set, just like we did in the previous section, we set the coordinates of the point we want to study. We calculate the distance, and we choose the data set at the closest distance, at the closest location of the point we have defined. We make sure that our script has worked. Yes, we are very close from the point we have selected. And then we can plot the time series. Just like we did for the map, I will show you first the results of the figure, and then I will show you how it's been constructed. So here is the results. On the bottom, you have the time, so the years at which the sea ice thickness has been measured. On the left, you have the sea ice thickness in meters. On the right, you have the minimap, which displays the location of the point we have selected. On the right, sorry. And on the left, you have the coordinates of the points we're studying. So how did we build this figure. First, we define the characteristics of the plot, the size of the figure. We add the grid lines. We set the title. We set a subtitle which displays the longitude and latitude. This line is used to clean the date times at the bottom. And then we use the plot function, and we're plotting in the x direction, we're going to have the time, and in the y-axis, we will have the sea ice thickness. These characters here are used to tell Matplotlib that we're going to have dots and not a continuous line. So this is an option if you want to have specific lines. The following lines are used to display the location of the point on the minimap here, and the last one, you save the figure. So that's it for the time series. We're now going to study a vertical profile, and to do so, we will use the in situ profiler. So a profiler is an instrument which measures the ocean parameters up and down through the whole water column. And so at several times and for several depths, you have the measurements of the ocean parameters. So here we're having a look at what the profiler contains. We're going to work with the salinity parameter. If you check, the salinity is stored under this name, and its dimensions are time and depth. So for plenty of date times, the profiler has measured has measured the salinity over plenty of depth. What we're going to do now is to select some index of measurements to consider. So here I've chosen the index 0 and 9, but feel free to change the indexes and to study some other measurements. In this line, you select the date. You retrieve the dates which correspond to the indexes that you have selected. Then you retrieve the location of the instrument for the index of measurements you have set. And then you get the actual measurements. And if we have a look at a set of measurements, for example, you can see that it's indeed the salinity. You can have a look at the time. At the time at which the instrument made the measurements. So again, let's see the results of the plot we're going to make. So on the bottom we have the salinity. On the left we have the depth. We have two lines which refer to the two indexes of measurements we have selected. We have the legend, which tells the date of measurements, and we also have the minimap again, which shows the location of the instrument for the measurements. So again, we were going to use the plot function from Matplotlib. This script is very close to the one we did before. We're just adding this line to invert the y-axis in order to have the surface, so the depth of 0 on the top. Then we display the minimap again, and we save the figure. So what we can see from this map is that the salinity is lower on the surface than at the bottom. And this is because the more salty a water is, the denser it is, and therefore the heavier it is, and the more likely it is to sink into the deep ocean. So fresh water is lighter than salty water, and this is why you have such profiles, very simply explained. Here is an exercise we suggest for you to manipulate the code. Again, you can change the the indexes of the measurements, and you can also change the line style if you want to plot some other features. In the following section, we are going to study vertical slices. And so the aim of this section will be to visualize how, well, let's take the figure, it will be easier to explain. So what we are trying to do in this section is to see how the salinity has evolved along this line and along the depth. So here, here is the line that depends on the y-axis. Here you have the depth. The color refers to the salinity. And here you have the time. So this region, for example, refers to this part of the figure, and the region on the east refers to this part of the figure. So how did we build this figure? We are using the function pcolor. So first we set the coordinates of the line. So here we want the x dimension to be 10. You can, of course, change the coordinates of the line and study any other region. Then the y coordinates will go from -15 to 12. Again, you can, well, feel free to change this. Then we are selecting the salinity. We use the dot cell method because x and y are dimensions and not coordinates. And then we select the first date time. We retrieve the date that corresponds to this first date time that we have set. Then we define the characteristics of the plot. We plot the salinity depending on the y-axis and the depth. We add the color bar, we set the label, we add the minimap, and we save the figure. So that's the result of the plot. As an exercise, you can try, as I suggested, to plot another line to see how the salinity has evolved somewhere else. And the last section will be dedicated to plotting animations. And so to do so, we're going to reuse the previous script in which, if you remember, we had selected the index of time 0. We're going to make a loop on this first script over all the dates that are computed in the data set. And so this is what we're doing here. We create a loop on all the dates, and here we select all the indexes one by one. And we create so plenty of figures for all the date times that are included in the model. And so we're going to plot the salinity for all the years, all the year 2020. Once you run this code cell, you will see that the figures are not displayed because of this line where we close the figure before displaying it. However, they are downloaded in the out folder here. And then the principle of this code cell will be to merge all the figures that we have created into a GIF file, into an animation. So you can choose the duration of each figure and how many loops you want to make. And so this is the result. On the top, you have the date, which refers to the figure. And so you can see how the salinity has evolved during all the year 2020 along this line and along the depth. So that was the last figure we were doing. It's been kind of fast, I think, but I hope you've been able to follow this first presentation. I hope you enjoyed it, and thank you very much for watching this. The aim of this exercise was for you to learn how to reach the Copernicus Marine Service products, how to load them into Python, how to explore them. And so if you are trying to do the exercises, and if you have problem with anything, do not hesitate to contact us through the service desk. We will be, again, very happy to answer your questions. And maybe, Fabrice, I have time for the presentation of the second book. Okay.
Yes, go.
Great. And so very briefly, I'm going to show you what the second notebook consists in. So just the result and what we have tried to show you. So the aim of this notebook was to explain how the thermohaline circulation works in the Arctic Ocean. So we are studying the currents in the Arctic Ocean, and we are trying to study how they have evolved in the frame of climate change. So again, we have plenty of explanation on the products, etc. But the figures I would like to show you are this one. So here, for a specific depth, a specific time, we can see how we have the map of the current, the temperature, and the salinity. And what we can see, a first observation we can make very briefly, is that the patterns of the current match the patterns of the temperature and the salinity, and this is because the current are mainly driven by the temperature and the salinity in this region. So especially here in this region, you can see that it matches perfectly with the other parameters. Then we are plotting an animation of the salinity and the temperature on a vertical slice, just like we did in the previous notebook. And so the aim of this figure is to understand that the cold water coming from the sea ice melting becomes denser and therefore drops into the deep ocean. So this is what we are seeing here, especially at this time. We can see very clearly that the mass of water drops into the sea. Then we are studying the current in the frame of climate change. And so first we compare the sea ice extent, the average of in summer 1990 to 2010, and then in summer 2010 to 2020. So obviously you all know that the Arctic suffers, well, the global warming is more intense in the Arctic Ocean than anywhere else in the world. So obviously we have fewer ice now that we used to have in summer in the years 1990 to 2010, sorry. And then we are having this graph to estimate the sea ice volume loss between these two periods. And so the result of this diagnosis is that we have lost 20% of the average volume between the two periods. And then we are trying to analyze the consequences on the thermohaline currents. So we're studying a very specific region. We're trying to see the time series of the the temperature to see that the temperature, we can see temperature has risen. The salinity, what we can see is that the amplitude of the salinity is decreasing. We used to have very high maximums and very low minimums, whereas now it's more, well, the difference is not as high as it used to be. And we're trying to see if the current velocity has, well, how it has responded to this change in temperature and salinity. And so this is what this last section does. At the end of this exercise, we suggest plenty of exercises for you again to manipulate the scripts and the product, etc. And so you have exercises dedicated to beginners, to intermediate level users, and to experts. Again, if you have some questions, if you have some trouble doing these exercises, do not hesitate to contact us. And also, you're going to have a debriefing session in which I will be back to answer your questions. So if you have time, you should have 2 weeks to go through the 2 notebooks and to try to do the exercises. And so if you have some question, you can either send us an email or attend the debriefing session, and I will be there to answer your question. So thank you very much for attending this first session. We'll give back the floor to Fabrice. Your mic is off, Fabrice, sorry.
Sorry. Yes, thank you, Ergane. Thank you for this presentation. I don't know exactly at which time we have the coffee break. I think we have time for some questions on Slido.
Sure, yeah.
Yeah, because a lot of people found this very interesting. So there is several questions on how to access.
Sorry.
I take the lead on the sharing screen. Okay, this is the question. So a lot of people wants to know how to access the material. So this is on the Padlet. Vincent, our technical guy, shared a lot of several times the link on the chat. So you can have directly the link on the Padlet to access the Jupyter okay. So the link to the material, this is again, how to access the Jupyter notebook again. Yes, it's on the Padlet, all this. Okay, could it be possible to add a graphical scale?
Of course, it's possible. I don't know if you mean. I'm not sure what you mean by graphical scale. Maybe
I don't remember at which part discussion refers. Okay, but perhaps the person who asked this question can clarify with a new question on Slido or on the chat, or you can also join Ergane in the breakout room to answer this question. Perhaps it's not clear enough to be answered.
I'm sorry.
Now.
Yes.
No
anyway, just to remind also the participants, if I don't have time to answer all your questions today, we will have a spreadsheet, Google Sheet, in which all the questions will be answered, and it will be available on the Padlet. So don't worry if we don't have time to answer everything.
The scale for the map, I think this is in this. So well, okay, need to clarify this one. Okay, sorry. Okay, for the part 4.5 subset the data, is it recommended to use decimal points to get closer to the point that we are interested in?
Yes, of course. You can use, I have set the values as integers, but you can use float. You can put as many decimals as you want. If you want a specific point, yeah, you will be limited by the resolution of the model, obviously, or of the product, but you can add as many decimals as you want.
Okay. Okay. The question about the scale was to have a scale in order to see the distances between the points on the map.
Right. I'm not sure. I think we had the longitude. You can add on the map the longitude and latitude difference. Otherwise, you have on the documentation webpage, you have
Yes,
the
you can
spatial
add
resolution, and it should be about 12 kilometers, I think.
You can add directly the grid on the.
Yes, you can add the grid as well.
Okay. If I have a shapefile specific to my study area, how can I insert or cut using Python script, please? Oh.
We haven't prepared the notebook, but I think we're going to do it for the Mediterranean Sea because on the training on the Baltic Sea, this was also a question that was asked. So I'm going to prepare this for the next workshop, but yes, it is possible with specific Python libraries.
Okay, so stay tuned.
Yes.
For the next training workshop dedicated to the Mediterranean Sea. It will be in May.
Yes, that's it.
In May or in June? No, in May. So in 4.7 part, what does the EDX index refer to? Is it a specific range of salinity considered for the plot?
The index refers to, well, the instrument has measured on plenty of time. I think the index refers to the date of time. So it has measured on date 1, on date 2, on date 3, etc.
Yes.
And so I have selected the 1st and the 10th indexes to have different values and a different location of the instrument. I hope this answers your questions.
Vincent, I continue to ask me to stop.
Yeah.
When it's time for the coffee break. Okay?
Yeah, you have 8
we can
minutes.
continue the questions continue to arrive, so I continue.
Yeah, you have 8 to 10 minutes. No worries.
Great.
Okay. Is it possible to access only the complete code without the narrative text? Yeah, perhaps it's to be able to copy only the code to create a new Jupyter notebook.
We haven't done it for now, but we can prepare you a Python script maybe.
Is it perhaps an option of the Jupyter notebook to be able to?
I'm not sure.
Okay.
I have never used it before, but maybe.
To be honest, it was my question. Okay. Is there a way to automate the workflow? I think it's possible not to launch all the cells.
Yes, it is. On the Jupyter Hub, if you go on Run, you can select to run all the cells. So yes, you have an option. You can automate the workflow. I hope this answers your question.
Yes. Are we going to finish all the questions before the coffee break?
Yes, great.
How long we will be able to use Jupyter Notebook, and can we use these case materials later on with some other system after downloading proper files?
Do you want to answer? The Jupyter Notebook will be available for a very, very long time, I think. So you shouldn't, well, we have not planned to put them off.
Yeah.
And so you can use them with your own files. You just have to change the path to the data and use as you want.
And don't forget to clone the Jupyter Notebook.
Yes.
From the public folder on your own workspace, on your private workspace, to be able to save all the modification you will make. This is very important.
And to clone?
Do not ever work on the public folder, otherwise all your modification will disappear. Okay.
And to clone the notebook, you have the explanation in the participant manual available in the Padlet.
Yes, exactly. Thank you, Vincent. Yes. On the user manual, you will see how to clone the notebook directly on your workspace. It's very important. And also you can download the Jupyter Notebook if you, in the future, want to install an offline solution like Anaconda on your computer, or use another Jupyter Hub on another platform. Okay. The OpenUp service is great, but it's very slow to compute graphs. Do you recommend to use this only for check the data?
So I completely agree with this question, which is why I prefer using the files that are downloaded. But this is not completely true, because if you want, well, for the most basic maps, if you just want to display a parameter on a map, the OpenUp service is very useful. But if you want to make advanced processes on your data, it's indeed easier to have it downloaded, because yes, streaming the product can take some time.
Yeah. I think we will have a breakout room with the service desk now
Yes.
at the end. So you will be able to ask this kind of question about the different data access during this breakout room. What about new satellite data?
So we've had a presentation yesterday of Cécile Vetre about the satellite observation data. She will come back on the debriefing session. So if you're interested in such product, you can attend the debriefing session and ask her the question.
Yes. And finally, can we print off the code?
I'm not sure what this means. If we can print the code from the Jupyter Hub.
I mean, perhaps, yes, if you can.
I think if you go to File, Print, it should work.
Yeah.
This is an option that, that is suggested in the Jupyter Hub. So tell me if it works.
Last question. Okay, and then this solver. This is a very last question. If I process data with MATLAB instead of Python, what data format is more suitable?
I would say that it's the netcdf file, because both MATLAB and Python can manipulate netcdf files very easily. So I think it's the easiest way for you to switch from MATLAB to Python. Okay,
so we process the data on MATLAB, we record the output in netcdf file, and then we reopen on Python to create the different maps, etc., etc. Thank you very much, Ergane.
Pleasure.
It's great. It's very great to have this kind of Jupyter notebooks. We try to provide you the e-learning material suitable for you, even you are a beginner or an advanced user. So don't hesitate to have a look to all this material. And on the website, there is other Jupyter notebooks available on other regions with other topics. So don't hesitate to visit this section of the website. So now, Vincent, is it time for the coffee break? Yeah.
Yes, it is. Yeah.
Yes.
Here we go. Okay. It's time to come back in the room, in the training workshop. So welcome back for the second part of this training workshop dedicated for the Arctic Ocean. And this session is focused on practical session, demonstration, and QGIS presentation. So after the great presentation of Ergane on Jupyter notebooks and for beginners, and the introduction of the Jupyter notebook for advanced people, let's dive now in the MyOcean Viewer Pro with David Bina from the Mercator Ocean International Service Desk team, who will present you the MyOcean Viewer. David,
yep.
Are you with us?
Yes, I'm here. Do you hear me?
Yeah,
yes.
Very well.
Okay, I will share my screen.
Okay.
Do you see it?
Yes, perfect.
Okay. So, hi everyone. I'm David from the Copernicus Marine User Support team. I will introduce you today our visualization tool called MyOcean Viewer, which is accessible from the homepage of Copernicus Marine. So I'm here on the homepage, and you can click on Ocean Visualization here, and it will open. It was already open here. This page, where we can see that actually there are 3 versions of MyOcean, globally speaking, corresponding to different user levels. So for beginners, intermediate, and experts. You have the main differences here at the bottom. I will quickly show you the first 2, and then we'll focus more on MyOcean Pro. So if I click on Explore MyOcean Learn, it will open this page where we can see the globe. Here on the left, you have the global oceanographic parameters like sea ice, salinity, temperature, current, chlorophyll, and waves. So I can click on salinity, for example. I can also click on play, that will display the variable versus the time. On this tool, you can move into the map, and you can also zoom in and zoom out like this. And that's it. There is no more action on this tool. Now, if I, oh, sorry, I see the zoom bar. How can I? Okay, it's okay. Now, if I open MyOcean Lights, we will reach this page where the global temperature is displayed by default. Once again, you have here on the left the global parameters, and you have at the bottom and the bottom right, you have the timeline and the depth range. So you can move through time, and you can change the depth level. So for example, if I go around 1000 meters below the surface, we start to see the bathymetry. You can move, and you can zoom in and zoom out also. And for this timeline and depth range, you can scroll with your mouse to zoom in and zoom out. That could be convenient, more convenient to select what you want, and you can reset the zoom. Once you are convinced that that's what you wanted to show, to have a look at, you can click here on the share button to share this page. So you can copy the link that will redirect here on this exact page. You can also create and download an image, which will be in a PNG format. You can create an animation video, and you can choose between the MP4 and the GIF format. And you have also the embed link if you want to share it like this. Okay, so that's it for this MyOcean Lights tool. And now, if I open my Ocean Pro viewer, sorry, we have by default once again the global temperature. We find again the timeline at the bottom and the depth level. If I stay on the layer here on the left, we can also see the product ID, the dataset, and the variable name, theta here. You can remove this layer if you want, or you can hide it by clicking on this eye icon. Here we are by default with the equatorial projection, but you can change into the south or the north polar projection. Because today we are interested in the Arctic area, I will choose the north polar projection. And I will start to add the products and the variables I want. So I click here on Add Layer. It will open the Copernicus Marine catalog. So we have nearly 200 projects to begin with. Here on the right, you have all the projects, so you can scroll to see all of them. But obviously, it's more convenient to use the filters on the left to select the projects and the datasets that we want. You can type a keyword here. I will show just after the favorites. You can choose between blue, white, and green ocean, corresponding to respectively physical, ice, and biochemical parameters. Then we have the main variables. You can choose between several fields, like ocean health or marine food. We can choose between the different areas, different time sources. As a reminder, Copernicus Marine provides 3 types of products. We have the numerical models and the in situ and satellite observations. And finally, you can choose a specific center and a specific processing level. So for this example, I will, let's say I'm interested in the sea ice thickness of Arctic Ocean. I can start to click here on sea ice. And as you can see here on the right or here at the top, we have 48 products left. Then I will choose Arctic Ocean and I will start with a numerical model. Just to show you, I will begin with this first product to show that a product can have several datasets. You can have the details of a product by clicking on the details button, which will open this detail page, which contains first a short description of the product, and here at the bottom, the DOI. Here on the left, you have the temporal and geographical extents, and then you have others metadata. If I click on Add to Map, here we can see that we have 2 different datasets containing different variables. Globally speaking, the differences between datasets are come from spatial and or temporal resolution. So here it's the same spatial resolution, but it corresponds to daily and hourly data. And then you can develop a dataset and see all the variables contained in it. But let me go back just where I was before, because I know that I want to choose a variable in this product. I can once again click on the detail button, but since I know that it's the product I want to select, I can directly click on Add to Map. And I know that I want to add the sea ice thickness here. So I click here on Add to Map. And just to show you that we can display at once several variables coming from several products and datasets, I will not choose another variable coming from another source. So I will choose satellite observations. And just to show you that you can add a product in your favorites once, you can click on the star here. And if I unselect all the filters I have selected before, and now if I click on favorites, I see that I have 1 now in this filter, and this is the one I've just added. I can click on details once again to see the details. And now I will add this variable, sea ice thickness. Okay, now I can close this window. And I will speak now about the customization parameters, because now we don't really see clearly the sea ice thickness. So let me zoom in just a bit. And I will start from the right, because it will be more convenient. So you can click on this cog icon to change the color map and also the value. So I will just let it ice because it's blue and it corresponds nicely to the ice. And now let's say that I will choose 4 for max value. It will appear quickly, I hope so. And just I will edit this one moment. If I click on log scale, we can also display the data in a log scale. But what if I choose 3? I will display it in log scale so we can see it more clearly, I think. Okay, let's choose the log scale so we can see it now more clearly. I will show this layer that was at the bottom. You can move all the layers down and up. So if I choose this layer to be displayed at the top of all the layers, we see it more clearly. Here, we can decrease and increase the opacity of the layer. So if I decrease slowly this layer that was on top, can you please?
Yeah, you can reopen your microphone, please, David.
Sorry, it's okay. You hear me?
Yes.
So here I have decreased the first layer at 0, so we can't see it. But okay, so it was just to show you that you can play with this opacity to see at once the two layers. I will click on log to see the difference. So here we can see the difference when I gradually increase or decrease the opacity. This button is really convenient. It shows all the variables contained in the dataset you have already selected. So let's say if I wanted to see the size area fraction of the dataset, I don't have to click again on add layer, open the catalog and do what I've done just before, but you can just click on this button and choose another variable directly from here. The I button opens the detail page we have just seen before. And I will speak just later about the download button. Okay, so let me just increase a bit this layer. Okay, so this is the observation one at the top. Here at the bottom right, you have several objects that you can place on the map. So I will place, for example, a point. You can draw a line, and also you can draw an area like this. As it's said on the tooltip window here in Cyan, once you have finished your area, you can press on escape button on your keyboard to finish your geometrical shape. So when you place these different objects on your map, as you can see, there are different graphics that appear automatically. These graphics correspond to the layers here that we see on the left. So let me just go it like this. These graphics, so there is the temperature. Even if you hide a layer here, the graphic will appear even if it's hidden. Globally speaking, for a point, you will have the timeline. You can delete and add other graphics. So for example, let's say that I'm not interested in this time series for the temperature. I can go here on the 3 dots and click on delete graph. And just to show you that for a point globally, you can have the depth profile for a variable that is in 3D, so which has a depth range. You can choose which type of graphics you want to display. And you click on add to graph. And now we can see the temperature depth profile. For a line, you will have basically the transect distribution of variables. And for an area, we will have the histograms of the variables. Just to show you here, under these different geometric shapes, you have the settings. So here I'm already logged in. Just as a reminder, you can display all these layers without being logged in. But afterwards, to be able to download or export the data, you have to be logged in. So you can do it from here. And you can play with different parameters for the map and the object. So you can show or hide the base map, the graphical, use a colorblind palette. So here, by default, as I've said before, we were on the equatorial projection, and now we are in North Polar. And you can also change the distance units. So you can move from kilometers to miles, for example, and play with others. Okay, now let's say that I want to export what we are seeing here for these graphics in a CSV format, we can do it by going again on this three dots button. And I have to highlight that even if we click on increase resolution, and by resolution, I mean temporal resolution, here we have selected a daily product, but if I click on export sample to CSV and I open it with Excel, if we just focus on the dates, we can see that we don't have daily data, but about one data per week. So just remind that it's more like a trend of the data and not the actual data when you export this data like this in CSV format. But of course, you can download the actual data you want to by clicking on this download button. It will open this canvas where you can process to a subsetting. You can define a geographic area, a date range, and also for the variables, for the three variables like the temperature. If I go on the temperature here, you have also the elevation range. But let's say that I want to download the ice thickness. I don't have anymore the depth level because it's only on the surface. You can, let's say that I want to download a subset from an area. I can click here on define on map and define an area directly like this by dragging my cursor. Or if I reset just to show you, you can click on define on map and click on an area already existing. And now you can see that the coordinates are automatically updated. Same for the date range. So yes, I forgot to mention that if I move through the timeline, all the graphics are automatically updated. And you can also move by grabbing this line here. It will change the date as well. And then you can choose the dates by opening the calendar or by choosing as in map. So now I'm in 21st June of 2021. Let's say just for the example that I want about 1 month or so for this area. Here, you will have a red warning because it exceeds actually the 1 GB limit. As it's explained just here, we can download at once only up to 1 GB of data. So here you have the warning if it exceeds this limit. So let me go back here and just, so it won't be too long for the presentation, go with 1 day. You have here the data size you're about to download. So here it's only about 30 megabytes, so it's okay. From MyOcean viewer, MyOcean Pro, you have 2 ways to download the data. You can click here on Show API Requests, which will open this window displaying the Motu client command line. If you don't know how to use Motu client, you can click here on this link, and it will open this article coming from the Help Center. The Help Center gathering multiple useful articles, and this one explains how to use the Motu client API. And also, sorry, it's this one. So I will close it. You can simply click on download here. So it will start to process the data. It will start the downloading. And since I have only 30 megabytes to download, it was very quick. And you can save your data locally on your computer. I won't do it, but that's the way how you can do it. If you want to download the data with other service, you can click here. Also, sorry, I was forgetting that once you have defined this subset option, you can also go back here to see all the variables contained in the dataset. And if I choose another variable, so the map is automatically updated. And you can just download once again with these two ways. It hasn't changed the subsetter. Okay, if you want to see the other ways to download data, you can click here on other download services, and it will open, this page, which is in fact the product page on the data access tab. As we have seen before, there is only one dataset for this product. And here on the right, you have all the API available to download the data. While I'm here, I can show you that here on the documentation tab, you have the technical and scientific documentation. So respectively, the product user manual and the quality information document. And if you go on information tab, in fact, we see once again the detail page that we have seen on MyOcean Pro with the variables contained in this product and other metadata. So to conclude, if you have any question or any feedback to share with us, you can contact us by going on this page, contact us. Or here at the bottom right, you can open the chatbot that will open this window. So you can search for article to find your answer. And if you didn't find the answer you were looking for, you can simply send us a message. And while I'm speaking about the chatbot, I can go back on MyOcean Lite just to show you that you can also click on this button, talk to an expert, and it will open the same chatbot window. So feel free to send us a message if you have any question or feedback to share with us. Thank you.
Thank you very much, David. Thank you. I thought at a moment you will be unstoppable.
But I am.
Once you are on the rails, but it's very impressive. This tool is very useful for all of you. At the beginning, David showed you the different visualization tools we have targeting different kind of users. But this one, the MyOcean Pro, is very, there is plenty of features you will like, you will see. And we try to regularly update this viewer, so be ready for the next version coming soon. I think we have two questions actually now for you. Yes, let's share my screen. Okay, do you see my screen clearly?
Yes.
Yes, so how to download long period, 10 years time series data at a specific location of each parameter.
So if you have, globally speaking, if you have a large volume of data that exceeds the 1 GB limit, you'll have to go to use the toolbox that is available, and you have an article in the Help Center that explains very well how to use the toolbox. You won't have the 1 GB limit with this toolbox, so feel free to check this article. Then you can type in the search bar large volume data, and you will find it really quickly. Because with this tool, you can't download data. I think 10 or 20 years of data will exceed probably the 1 GB limit. So you will have to use the toolbox.
Okay, thank you, David. Thank you, very nice tools. Is the PNG geo-referenced?
So I guess it's about when we create an image.
Yeah, I think.
Honestly, I don't know. I don't have the answer. But and I'm not sure I understand how an image can be geo-referenced.
Yes, yes.
What does it mean? Does it mean that within the image we see the CRS or something like this? Honestly, I
When you have a georeference file, you can upload it on any visualization tool, and automatically it will be positioned at the correct place. But I'm not sure the PNG of this tool is georeference. I'm not sure even we can georeference a PNG, but okay.
Yeah, I don't think so.
Don't hesitate to come during the debriefing session to ask the question. We will make some research on this question.
Yeah.
We will have the answer at this moment during the debriefing session.
Yeah, sure.
Okay. Thank you. Thank you very much, David. It was very clear. Well done.
I hope so.
So it's time to continue our training workshop. It's now the turn of Etienne Sahuc, oceanographic engineer at Noveltis, to present the QGIS tutorials focused on the Arctic region. Etienne?
Yes.
Are you here with me?
Hello, Fabrice.
Hello,
Yes.
Etienne. Okay, I'll let you sharing your screen.
Okay. So hello, everybody. I'm going to show you some exercises on the QGIS software in order to treat some NetCDF files and products from the Copernicus Marine Service. First of all, I'm going to share my screen. So here we are on the QGIS software, but first of all, I'm going to do a short introduction. As we are working with the Arctic region, we know that the Arctic covers a vast area, most of it being uninhabited. The human infrastructures are scarce and are certainly not spread enough to precisely track the rapid changes occurring in this environment. As the region is warming up twice as fast as the rest of the world, it requires a more intense monitoring, and models are also need models in this zone also need reliable observations as inputs to provide the most accurate estimation. This is why and where space-based technologies have a key role to play. In this context, the operational, precise, and reliable Copernicus Marine Service products for the Arctic are a great asset to analyze and forecast the sea ice concentration and conditions in this region and assess the state of the sea ice layer in near real time. In this tutorial, I'm going first to show you a beginner tutorial to teach you how to display several layers of sea ice thickness, sea ice concentration, and vector fields on the QGIS plugin. And then on the second exercise, we will see how to compute climatology of sea ice extent on the Arctic region and check the slope of this kind of graph information with the huge decrease of the sea ice extent in the Arctic for the month of September, according to the NSIDC. So first of all, I'm going to go back to my QGIS project. And here, this is a new project. And as we are dealing with...
Sorry, Etienne. Can you share your screen?
Oh, sorry. Okay.
I thought it was just an introduction without...
No, but it's okay now.
Okay.
As it is a new project and we are working with Arctic data, these data are using polar projection with curvilinear grids. So we'll see how to reproject these products in our QGIS project. So first of all, when you have opened your new project on QGIS, we are going to open the NetCDF 2GIS plugin, which is available on the Padlet of the Copernicus Marine Service, and which enables to treat with NetCDF files available on the Copernicus Marine Service platform. Here, I have the netcdf2 GIS plugin opened, and we are going to reduce it and deal with projection, and then we will go back on this plugin to load data of interest. First of all, we are going to work with the Arctic region. So we are going to set the main projection of our project to north stereographic projection. So if you go to the PSG here and select the CRS, the coordinate reference system here, you can select the North Pole stereographic projection, or you can look at it by typing this code here. All the information to download the netcdf2 GIS plugin and to follow the steps of this training are available on the user manual provided on the Padlet of the Copernicus Marine Service. So here you can click on Apply and OK. Now we are going to import backgrounds to this project to add a map as a background. So to do that, we are going to layer, add layer, and we are going to add a WMS layer here. Here you just have to connect to the map server demo, which is providing several layers of backgrounds. So we are just connecting to this server. We are going to use the blue marble layer, which is a good background layer for our project. Here, before adding this layer to our project, we are going to project it on a specific CRS projection, which is Canada Atlas Lambert. And just click on Add. Here, a new window, which is a transformation window between the Canada Atlas Lambert and the North stereographic polar projection of your current project is opening. So you just have to click on OK. And then you can close this window. You can see that on the background of your layer, of your project, sorry, if you zoom, you have a North polar view of the map of the world. Okay, and we are centered on the Canadian meridian, on the Canada Lambert projection. What we can do now is to go back for our main project to the projection of North Pole stereographic and click on Apply and OK. It can take some time, but it's gonna project this layer to the main project layer. And now we have a North Polar projection centered on the North Pole, and we are aligned with the Greenwich meridian. Now we can start importing some data to this project and see how to visualize information from the Copernicus Marine Service. To do so, just open the netcdf2 GIS plugin and click on plus icon here to import the first data. I'm gonna look for my files, and then we can select the file, the netcdf file containing chlorophyll informations from the biogeochemical products from the Copernicus Marine Service. So here I'm going to import daily data from the biochemical forecast model from the Copernicus Marine Service with a spatial resolution of 6 kilometers at the North Pole, and data from September 10th to 15th during the 2021 year. Here I'm selecting this data, okay. And here in the netcdf2 GIS plugin, I have access to several informations. First of all, I have access to all the variables of my netcdf file with the dimensions, units, and the long name of each variable. And also on metadata, I have access to the resolution of each product, to the projection norm, as if we can say that. And this is really important for the following of this session. And we have several global attributes about the origin of these products. So here, for example, I will display the chlorophyll concentration over the Arctic region. So I select my chlorophyll variable here, click on Add Layers, right-click on my layer and select Add Layers. And here I'm going to import all my layers from the 10th of September to the 15th of September. I select the first layer, press the Shift key on my keyboard and select the last layer. And I can click on Add and Close. So all my chlorophyll layers have been added to my layer panel here, but you cannot see already these layers on my main project, and it is because they are not projected on my North Pole stereographic projection. So what we can do now is to just reproject these layers on their own projection, and then we will see it on our project. So to do that, I'm going to select the settings option here and select custom projection in order to manually add a projection corresponding to the Copernicus Marine Service polar projection. And then I can see my layer on my QGIS project. So for example, I will add a new projection, add a new CRS that I will add manually. I can call it Arctic Stereo Training, for example. And here I will change the format to define this projection to ProjString. Now I can come back to my NetCDF to GIS plugin and metadata of my first NetCDF file, and I will copy this projection here in the metadata of my NetCDF file. I will paste it here and just remind here to change the coefficient K to 0.00001 in order to convert kilometers to degrees. So here we are converting X and Y coordinates of the polar grid of the Copernicus Marine Service products to longitude and latitude coordinates. You can click on OK. And now we are just going to change the coordinate system of each layer here and set it to the one we have just created now. So if you right-click on all your layers and select Layer CRS, you can select Set Layer CRS here. And you can browse to the bottom of all the coordinate reference system and look for the user-defined coordinate system. And here you have access to all the coordinate system you have created. And so the last one was this one, Arctic Stereo Training. So I'm going to select this one. Now you can see that your Arctic products are visible over your map with the North Polar stereographic projection of your main project. What we can do now is to just change the style of these layers. So to highlight chlorophyll A blooms and I concentrations. To do so, what we can do is to just go to the properties of our layer and right-click to our layer to open its properties. So here, I right-click on my first layer and open the Properties tab, and I'm going to change the minimum and maximum value of my chlorophyll A concentration layer. So the minimum value is set to 0.5, and the maximum value is set to 9 milligrams per cubic meters. I will just invert the color ramp to have minimum values in blue and maximum values in red. Here you can click on Apply and then OK. So we can see if we center our visualization panel, that we have chlorophyll blooms here in the Bering Sea. And we want to see the evolution of the chlorophyll A concentration during the first week of September. So we are just going to copy the style of this first layer with this chlorophyll A concentration values, copy the style of the first layer and apply it to the remaining layers. So I select all the layers with Shift on my keyboard, and then I can just paste the style of the first layer. Now we have access to the evolution of the chlorophyll A concentration just by scrolling between all our chlorophyll A layers. For example, we can see that the concentration of chlorophyll A is blooming here in the Bering Sea, for example, and reducing south of Iceland here. In comparison, if we advance in time. So that was the first part of this this training. Now, now we know how to display a layer of some variables over the Arctic and to reproject it. Now we are going to use an additional data from the OSPAR Commission to show you how to extract some data from a layer on a polygon. So here I'm going to import my OSPAR Commission polygon defining maritime areas. So this layer is available on the EdModNet portal, and all the informations to download this layer are available on the user manual on the Padlet. So I can select add layer, and we are going to add a vector layer. Here we are going to go to our data, and in EdModNet, I will load the shapefile of the OSPAR convention here. Click on open and add. If I close this window, now I can see that my shapefile have been added to my project here with several polygons defining maritime regions over the Northeast Atlantic and the Arctic region. I will just drag my layer on top of the others. And here I can just change the representation of this OSPAR Commission polygon. Here I can just select the outline red contour representation, click on apply and OK. So as you can see, we have several polygons, but we want to select only the Arctic region polygon here and extract our chlorophyll A concentration data on this polygon. To do so, we will just right-click on our polygon layer and select filter. And we are going to apply a filter about names. So double-click on names. And here, we will just filter the name of the... We will filter this polygon by name, applying the name equals maritime region corresponding to Arctic. To do so, we can just here make a search for all the names of the values of this polygon. And here you have each region. And we are just going to set the test to name equals OSPAR Maritime Area Region 1 here. Here we can click on OK. And only the good polygon is remaining. Before extracting some data on this polygon, we will check the validity of this polygon. And to do so, we will use some function from the toolbox. So open the processing toolbox. And here we are going to use a function that ensures that polygons we are using are valid. There are no geometries issue. So first of all, we are going to select the check validity function and apply it on our OSPAR polygon here that is already loaded as input layer. And for example, you can click on run and then close. Here, as you can see, all the polygon of the OSPAR convention, the Arctic region, is corresponding to invalid output, sorry. So we need to correct this polygon. To do so, you can remove the analysis polygons here. Right-click on it and remove layers. Okay, and we are going to apply a correction to our polygon. To do so, you just have to look for the fix geometries function and apply it on the same polygon, the OSPAR convention polygon here. So you can create a new temporary layer, or you can save the file to, for example, OSPAR convention polygon underscore fixed as a shapefile format, and you can click on save. Now you can run this function, and QGIS is then correcting the geometries of your polygon. It can take some time. And we need to correct our polygon before extracting some values on it to avoid several issues on the following of this exercise. So it should be done quickly now. Okay, now it's okay. You can then close this function window. So here, if we deactivate this window, here we have a fixed polygon. So we can proceed to our extraction. So we are going to extract the value of this raster, for example, the chlorophyll concentration on the 10th of September on this OSPAR convention polygon fixed. To do so, you are going to raster and select extraction, and then we are going to clip raster by mask layer. So our input layer is the chlorophyll concentration on the 10th of September. And we are going to use the mask layer, which is the OSPAR convention polygon fixed. Now you can click on run. Okay, so I have an issue with the memory on my computer, so I just need to change the parameters. So here I'm going to save the clipped mask to another file. So for example, I will save it here. So here it is the extraction of chlorophyll A. So you should be able to extract this this window. I will shortly make some space on my computer. I'm sorry for this issue. Maybe I can.
Don't worry, Etienne. Take time to clear some storage. If you need, you can stop sharing your screen for 1 minute.
For a minute. I'm sorry.
just to, I take the opportunity to say that it seems that we had a technical problem with Slido, and we received a lot of questions for David, but with a delay, so we could not answer the question live. So don't worry, because we collect all the questions you ask on Slido, and all the questions will be answered during the debriefing session. And if you need the answer quickly, don't hesitate to contact the user support at servicedesk.cmems@mercator.ocean.eu. You have the address on the chat. Okay. So, Etienne.
Okay, I just will retry my extraction.
And just to say that you will have the video tutorials also for the QGIS tutorial available on the YouTube channel, and with the link on the e-learning material platform, the e-learning material section on the website. So this is some technical issues. When you are a trainer, you have a lot of data on your computer, and sometimes, okay, it happens. You don't have enough resources to make your demonstration live.
Yeah, I'm sorry, but I cannot find
don't worry.
why it's not working. Well, I'm going to switch to skip this part maybe, and go on the following. All the steps of this training are available on the user tutorial, so you can follow them on your computer at the pace you want.
Yes, there is some questions already on Slido about the plugin. You can go directly on the Copernicus Marine Service website on the e-learning web pages, and you will find the information about this plugin and how to download it and how to install this plugin. Be careful, because there is different ways to install QGIS to be sure that the plugin will run smoothly. So check the different requirements on the website. Is it okay, Etienne?
No, so
No.
I'm going to skip this part maybe. I hope the following part will be okay. So I will share my screen again and go on the following part.
Okay.
No problems. So if you are at this step, you can just click on run on your computer. It should work, and you will end with an extraction of this layer on your of the chlorophyll A layer on this polygon. So the second part of this training is how to display sea ice concentration and how to display a vector field. And we have selected the sea ice drift vector field. So these data are extracted from the Arctic analysis and forecast physical model.
Can you just switch on your camera? Yeah. Thank you.
Okay, can you see my screen?
The screen is okay, and your camera is on.
Okay. So this model have a spatial resolution of 12.5 kilometers at the North Pole. And we have downloaded it on Norley mean temporal resolution. And we are going to see and display the fields on the 4th of March 2022 from 10 to 3 p.m. So here, as we did before, we are going to load layers individually. For example, we want to display first of all the sea ice concentration. So we are going to select this variable and select add layers. Here we can select the first layer on the 4th of March 2022 and click on add and close. As you can see, we cannot see it already. We are first of all going to uncheck the OSPAR polygon and the chlorophyll A concentration layers. And here we just need to change the CRS to display our layer on our project. So right click on it, go to layer CRS and set layer CRS. And we are going to choose our CRS we have manually edited at the beginning of this training. Then you can click on OK. Here you can see that there is the sea ice fraction represented on this panel. And we are going quickly to open the properties of this layer. Here we are just going to set the minimum value to 0, a concentration of 0%, to 1%, to 1, which corresponds to 100% of sea ice. Here just invert the color ramp and click on apply and OK. Okay, so we can see that on the 4th of March at 10, there is a sea ice concentration of 100% all over the Arctic region, here on the Canadian archipelago along the Greenland coasts. And we are now going to display the sea ice drift over this layer. To do so, go back to the plugin, the NetCDF2GIS plugin, and here we are going to load each layer that compose the sea ice drift vector field. So we are going to import sea ice velocity along the eastward axis and along the northward axis. So select the first variable, click on add layers, and for example, we are going to display the vector field only for the 4th of March at 10. You can click on add and close, and here select the second variable, click on add layers, and then add and close. So here we are not seeing those scalar fields on our project, but we don't mind because what we want to display is the vector field. I'm just going to change one option. Here you have options of the plugin, so I'm going to change my my directory of work. Maybe it will solve my issues. Okay. And now, if we go back to the layers we have imported before here, we have the U component of sea ice drift, the V component of sea ice drift, and we are going to select both of them by pressing Ctrl on my keyboard. And here you have access to the several function of the plugin, and there is the vectorize option here. So we are going to vectorize our two scalar fields using a UV components norm. We are going to select each component corresponding to U and V, and we are going to use the current norm here to display the vectors on the good direction. We are going to apply a downsampling factor, which is a factor to reduce the number of arrows on our map. And I will choose a downsampling factor of 10, sorry. Here on the output directory, just select where you want to create your vector field, and then you can rename your vector field. For example, CI drift on the 4th of March, and then you can click on vectorize. So here, your vector field has been computed, and to see it on your map, you need to change the representation again of the coordinate reference system. So right-click on your vector field, go to Layer CRS, and set Layer CRS to the Arctic stereo training we have created at the beginning. Click on OK, and now you can see that you have access to several arrows on top of your CI's concentration layer. What we can do now is to just change the style of these vectors, importing a style file we have been preparing for you. So you can just open the properties of your layer, and we are going to load a style file in order to represent the values of the CI's drift. Here you can click on style at the bottom of the properties window and load style. So we are going to load a style from a file and just browse to the directories and look for the directory where you have the CI style .qml, which is provided with the user manual on the Padlet. Here you can click on open, load style, and apply. Once it is done, click on OK. And here you have access to your vector field over your CI's concentration layer on the Arctic region. So we can see that the higher CI's drift vectors are at the extremity of the CI's concentration, which is near 100%. So where the ice is breaking, and the maximum values are here on the Labrador Sea and here on the eastern coast of the Greenland. So that was the demonstration for the first part of this training, for the beginner part. So we have seen how to display several variables on QGIS from the Copernicus Marine Service of chlorophyll or any other layer, CI's concentration, for example. And in this last step, we have seen how to compute a vector field in our NetCDF2 GIS plugin, and to draw maps like this one with CI's concentration and vector fields. Now we will switch to the advanced exercise, and I will show you quickly what we are going to do in this advanced exercise. Remind that all this material is available on the Padlet, on the Copernicus Marine Service platform. So you can try to do these exercises. And if you have any question, just ask it in 2 weeks during the debriefing session. So for my advanced exercise, I will just here uncheck all my layers, and I will import new data for this new exercise. So first of all, we are going to import data corresponding to CI's concentration from 1993 to 2010, which is extracted from the Arctic multi-year physical reanalysis model from the Copernicus Marine Service, with a resolution of 12.5 kilometers again on a curvilinear grid. So we are going to open this file. And here we are going to deal with the CI's concentration. We are going to add layers. And here we just want to focus on the month of September, which correspond to the end of the Arctic summer, where the level of sea ice is at its minimum. So I'm going to select here with the control key on my keyboard all the months of September during the 17 years we have been selecting. So in the NetCDF2 GIS plugin, you can select only some layers, and that's really easier than on the basic method for QGIS. Okay. Now we are going to import these layers as the CISCons group. You can click on Add and Close. And when it is done, we are just going to reproject all these layers in order to see them on our window. So select the Arctic Stereo Training here, projection. So as you can see, during the month of September, the sea ice concentration is only at the center of the Arctic region because it is the end of the summer. And now we are just going to compute the climatology during all these 18 years. To do so, we are going to apply a calculation on all these layers. So we are going to open the raster and raster calculator here. And what we can do is apply operations between all these layers. So we are going to compute an average of sea ice concentration during the months of September from 1993 to 2010. The expression is already filled on the user manual, so I'm going to just paste it. So as you can see, we are just summing each layer of sea ice concentration and just dividing by the number of layers. You can just change the output layer and, for example, call this climatology from 1993 to 2010 V2 because I have already done it on my computer. Click on save and click on OK. So if you drag your climatology layer on top here, you can see that it is in black and white. You can just change the properties, change the render type to single band pseudocolor to have it in colors, and set the minimum value to 0, the maximum value to 1, corresponding to 100% of sea ice, and invert the color ramp from blue to red again. Click on apply and OK. Now we are just going to multiply this layer by 100 in order to change the value range from 0 to 1, corresponding really to 0 to 100%. To do so, again, we open the raster calculator and we apply the multiplication by 100 on this layer here. So multiply by 100. Here, just change the output layer to climatology 100. Save and just click on OK. Again, this layer has values from 0 to 100, and we just change the properties, switch to single band pseudocolor 0, here 100 to the maximum value, and invert the color ramp. Click on apply and OK. So here we have computed the climatology of sea ice concentration from 1993 to 2010. What we can do now is to filter this layer in order to compute the sea ice extent. First of all, because we want to extract the sea ice extent of this period, and the sea ice extent is defined as all the pixels of the model where the sea ice is covering at least 15% of the pixel. So in order to filter this layer, we need to convert it to a polygon format. So we are going to select raster here and conversion. We are changing an SCDF file, a raster layer, to a polygon file. So click on polygonize. Here we are selecting the climatology 100 layer, and we are going to create a new field on our polygon, which is the sea ice concentration. Okay, now we can just select the output name here. And we are going to call this layer climatology polygon with the shapefile format. Click on save and run. Okay, hopefully it is working now. We have now, if we close this window, a climatology polygon. We need to change the layer CRS to have it on this principal window. So Arctic Stereo Training CRS. And here you can see that you have polygons corresponding to each level of sea ice concentration between 0 and 100. What we can do now is to just filter this polygon layer, climatology polygon. And in order to keep only sea ice concentration higher than the threshold of 15% in order to consider it as sea ice extent. So again, right-click on your layer and apply a filter. And here we are going to filter the sea ice concentration, which are higher or equal to 15%, our threshold. You can click on OK. And you can see that this polygon is corresponding to your raster layer, where sea ice concentration is represented in red and yellow over the 15% threshold. Now, the last step of this exercise is just to fix our geometries, because here there are some invalid geometries, because we are working with polygon and it's always the case in QGIS. So you should every time check your polygons and fix them. So I'm going to apply the fix geometries function to my climatology polygon layer, which have been filtered. Then you can click on run and close. So here I have all my fixed geometries. So these polygons are representing my extent of sea ice for the period between September 1993 to September 2010. The last step is to merge all these fixed geometries. So I'm going to click on Vector Geoprocessing Tools and Dissolve. And we are going to dissolve fixed properties here. Click on Run and then close. Here we have the sea ice extent of the period for the climatology. We can now rename this layer and call it sea ice extent for the period 1993-2010. What we can do is to compute the area of this polygon in squared kilometers. To do so, just right-click on it and open the attribute table. Open here, click on the pen icon to toggle to editing mode, and select field calculator here. What we can do is to create a new variable, area squared kilometers, which is using the already existing variable area in QGIS, and we are going to multiply it by 10 exponent minus 6. Click on OK. And now you can see that the area of this sea ice extent for the climatology between 1993 and 2010 is almost 7 million of square kilometers of sea ice. Now we are going to display the sea ice extent for the year of 2020, and we will see how much sea ice, how much kilometers, square kilometers are covered with ice. So now you can just close the editing mode and save the modification you have done. And in this next step, we are going to use the other file, netcdf file containing sea ice for the month of September 2020. Click on Open. Here again, we are going to add this layer corresponding to the month of September 2020. And here you can just change the group name to sea ice concentration 2020. Click on Add and Close. Reduce the netcdf to GIS plugin window and change the layer CRS to display your new layer. Okay, we can just change here and uncheck all these layers in order to only keep the polygon representing the climatology sea ice extent. Now we are going to apply another method to filter sea ice concentration higher than 15%. So directly we can open the raster calculator. We don't need to compute an average because we have only one layer, and we don't need to convert it from 0 to 1 to 0 to 100, and we can directly apply a filter. So in this new layer here, I select the sea ice concentration for the month of September 2020 and apply higher or equal to 0.15, our 15% threshold. Here you are just changing the output name and click on OK. So now in this resulting layer, you can drag it on top. You have only 0 and 1 values. The 1 values are corresponding to the sea ice concentration higher than our threshold of 15%, and 0 values are below our threshold. So they are in red, in white and black. And the next step is to convert to only filter, this layer with values equal to 1, so values higher than 15%. To filter a layer, we need it at polygon format. So what we can do to convert raster to polygon, we are going to use raster conversion and polygonize. We are using the sea ice 2020 layer here, creating a new field for our polygon, sea ice concentration again, and click on Run. Okay, now we have a polygon with several elements here for 1 values and here for 0 values. We are just going to filter this polygon, and we are going to apply a filter on sea ice concentration higher or equal to 1. Click on OK. So we are only, if we deactivate this raster layer here, we are only keeping the sea ice concentration which are equal to 1, so higher than 15% of a pixel. Now we are going, once we have filtered our layers, we are just going to merge all the polygons which are equal to 1. To do so, we are going to do again vector geoprocessing and dissolve on our vectorized layer here. And we are just going to change the output file to sea ice extent for the year of 2020 at the shapefile format. You can click on save here and run. Here again, we need to change the layer CRS to the one we have made at the beginning of this tutorial, Arctic Stereo Training. And we can just uncheck this vectorized layer. So here, if we deactivate the sea ice concentration raster layer, we have the difference between the sea ice extent in 2020 in red and the sea ice extent corresponding to the climatology between 1993 and 2010 in brown. So we can see that the reduction is huge between the two periods on the sea ice extent for the month of September on the Arctic region. We have seen that on this sea ice extent for the climatology, the extent was almost 7 million of square kilometers, and we are going to compute the area covered by ice in this layer corresponding to 2020. To do so, right-click on the layer and open the attribute tables. Here, again, we need to open to toggle to editing mode and open the field calculator. Again, we are going to call this new field area squared kilometers and apply the conversion to squared kilometers. And now the results of the area covered by sea ice concentration higher than 15% is almost 4 million of squared kilometers. So the extent covered by sea ice between 1993 to 2010 and the last year, the year of 2020 have been reduced by almost 3 million of squared kilometers, as we can see on this map. So this exercise is really, really interesting on how to compute this kind of sea ice extent reduction on the last years. So we have seen how to import data from the Copernicus Marine Service dealing with sea ice concentration. Of course, we are in the Arctic region, so it's really interesting to deal with sea ice. And we have seen how to have some comparison, really interesting comparison between climatology and minimum sea ice extents as have happened in the 2020. So in the end of this training, there are also other exercises on sea ice thicknesses. So I invite you to follow these exercises on the Padlet with all the user material needed, and then come back in 2 weeks for the debriefing session. If you have any questions or comments on QGIS, on CMM products, on the NetCDF2 GIS plugin, or on exercises like this. Thank you for your attention. Sorry for the little problem on the first steps of this training, but you will find all what you need on the user manuals. Thank you.
Thank you very much, Etienne. I think a lot of people found this very interesting. We have 3 questions for you. Yes. At the moment. I will check on Slido if we have other kind of question available. No, not for the moment. So the first one, I would share my screen. Sorry for that. Screen 2. Okay. So We see your QGIS already plugged in, but if we want to plug, how we can do it, please?
So you will find on the Padlet again all the informations. There is a user manual on how to download and on to install the NetCDF2GIS plugin. So you can download it is a zip file and then easily install it on your QGIS. Be careful to download the good version of QGIS with OSGeo.
Yeah.
So maybe you will have some issues, but they have been solved and explained on the user manual. So you will find all what you need on the Padlet.
Okay, perfect. So the second question was exactly the same.
Yes, the plugin is NetCDF2GIS plugin.
Yes. Is there a way to automatically select the month of September for all the years instead of clicking manually each of them?
No, unfortunately, you have to click for each month. Maybe on the Copernicus Marine Service, we could subset each month of September. It could be good because I'm downloading all the data before using them on our training exercises. So just so you know, but no, there is no shortcut to select only September months or so on. Maybe you can, before importing your data on QGIS, you can apply some modification with the CDO or NCO, which are tools in command lines to make modifications on NetCDF files. And then you can select only September months and then import them on QGIS, but maybe it's not the easiest way.
Yeah. So just we can have a look to the Padlet to see. Okay, there is a QGIS tutorial here. Okay, so don't hesitate to have a look on all this material. Okay, and then I think it's the end of this second day of the training workshop. Dedicated for the Arctic Ocean. I would like to thank all the experts who prepared the session. Ergane Fouchet as the moderator and the presenter of the first session on the Jupyter notebooks. David and Etienne for their presentation on the MyOcean viewers and QGIS tutorials. Also, thank you to Vincent for the technical issue solved. So it's time for us to leave you. I think we have the debriefing session in the end of April, the 28th of April. So we look forward to seeing you during this session. Waiting for this session, don't hesitate to have a look to all this material available now, from now on the Padlet and on the Jupyter Hub and on the website. Thank you very much to all.
Thank you.
Before we leave, maybe we can all switch on our cameras.
Yes. And I will stop sharing my screen. Okay. So thank you, David. Thank you, Vincent. Thank you, Etienne. And thank you, Ergane. Have a nice evening and see you during the debriefing session in 1 week, few weeks?
2 weeks.
2 weeks.
2 weeks. Bye.
Bye, everyone.
Bye.
Thank you for being here.
Thank you, guys. Thank you very much.
Thank you to all.